Hi everyone. So in this video I'll be talking about confidence intervals. So the point of a confidence interval is to be able to construct an interval estimate of a particular population parameter. So without loss of generality, I'll just discuss the population mean. So confidence intervals are built such that it contains the population mean with a particular likelihood. For example, with a 95% confidence interval, our confidence level is 95%. And this has the interpretation that if we were to construct a large number of similar intervals, similar in the sense of applying the same method to build the interval repeatedly, then 95% of them would contain the true population mean. So again, that's the frequency approach to interpreting probability. Confidence intervals are random intervals now in the sense that each new sample will produce an interval with different endpoints. So why is this the case? Well, each new sample is going to, of course, have different sample statistics. So every different sample is going to have a different sample mean, and of course, having a different sample mean implies using different boundaries for the interval. And every confidence interval is of the same form, it's just centered on the sample statistic. For instance, the mean, and bounded on both sides by a distance equal to the product of our stated critical value and the standard error of the sample statistic. In this case, we'd have the standard error of the mean. So I'll talk more about this a little bit later on in the video. The randomness inherent in the confidence interval is a characteristic of the procedure used to generate the interval in the first place. So the idea is that there's a 95% chance that the interval will contain the mean before the sample is drawn because this is a likelihood of the function, because this likelihood is a function of the method used to construct confidence intervals. So a 95% confidence interval is an interval estimator specifically constructed such that 95% of them contains the true population mean. So let me talk about large sample confidence intervals. We would use a large sample confidence interval under the following conditions. We would need to have a normality property that's of the sampling distribution that's guaranteed either by virtue of the central limit theorem or by virtue of having a normal population. So we would need a normal population or that the sample size is sufficiently large, bigger than 30. And if these conditions hold, then we can construct a large sample confidence interval, which is of course just the sample mean plus or minus the product of our critical value times the standard error. So with a large sample, we would use z-scores as our critical value, and we would use the population standard deviation in our calculation of the standard error. Well, suppose we don't have the population standard deviation. What would we do then? Well, we would then use the sample standard deviation because it's the best we could do. And we would use it to try to infer something about the spread of the population on the basis of the spread of the sample that we've drawn from it. If we have a relatively small sample size, we're also forced to use the t-distribution for our critical values. However, for large sample sizes and for unknown population standard deviations, it won't matter a great deal if you use the t-distribution or the standard normal distribution for critical values because for large samples the t-distribution is itself approximately normal. So here's an example of a large sample confidence interval with a known population standard deviation. Basically, we're just plugging the values into the general form for a confidence interval that I showed a few slides ago. The only thing that's really different here is that I've written the result in true interval notation. And that's because that's really what statistical software would report, the actual interval with parentheses and then a comma. This thing right here that looks like an E, that's just the mathematical notation to indicate that this mu is an element of the interval or is contained in the interval. And of course that's only true for 95% of similarly constructed confidence intervals in the long run. Now, suppose we have a small sample size and the population standard deviation is unknown. Presumably that's because the original distribution was not normal, or the sampling distribution fails to be approximately normal because we haven't satisfied the n is greater than 30 criteria to be able to apply the central limit theorem. At any rate, we need to use the t-distribution in order to build our confidence interval. Well, the sampling distribution of the t-distribution looks very similar to being approximately normal. It's still symmetric and bell-shaped with mean 0, but it's lower in the middle and it's got taller tails. The point is to be able to account for the fact that smaller samples have a tendency to produce distributions of this shape. You can actually get a sense of this by doing some repeated sampling from a general distribution in Minitab and watching to see what happens to the sampling distribution with, say for instance, a sample of 5 versus a sample size of 50. The n equals 5 case will be much lower in the middle and then have higher tails than would the n is 50 case. And that's just characteristic of the t-distribution. Or that's the foundational logic for the t-distribution. Now the t-distribution is specified differently for each sample size, and that's the whole point. The standard normal distribution with mean 0, standard deviation 1 is the same for all sample sizes. So to find the probabilities, we would just use the z-score and we'd have the same table for every sample size. Well, for the t-distribution, we need to find the number of degrees of freedom and the percentile we're interested in order to be able to locate the particular probability on the table. Well, the number of degrees of freedom, that's just one less than the sample size. So in my example, supposing we want tail areas of 2.5% to place a total of 5% combined in the tails and 95% in between, we constructed the basis for a 95% confidence interval. And to be able to find that probability for a sample size of 5, we would need to use the t-distribution with 4 degrees of freedom. The associated value would be 2.776, which is actually analogous to the z-score of 1.96, right, for a 95% confidence interval. The confidence interval we build from the t-distribution has the same general form as the one we saw earlier. It's a sample mean bounded below and above by the product of a critical value and a standard error. Here we use the sample standard deviation and the critical value from the t-distribution. That's the difference. Suppose, for example, we have a random sample of 25 and a sample mean is 50, the sample standard deviation is 8, and we want to construct our confidence interval. We can just plug these values in and have our small sample confidence interval built here. What's missing is, well, we need the critical value that places 2% in each tail area with 24 degrees of freedom. So we'll go look that up in the table. The value we need is this 2.064. Now think about how this value of 2.064 compares to the value I showed you earlier with 4 degrees of freedom. That's 2.776. I'll talk a little bit more about this later on, but reflect on why that's the case. Okay, so just to recap, for large samples we use the normal distribution from the central limit theorem, or by the central limit theorem. For a 95% confidence level, we would use a critical value of 1.96. We might also want to use the empirical rule just as a quick and dirty general guideline. In that case, we'd build our 95% confidence interval using 2 as the critical value. So technically that's incorrect. You're not going to see this very often in reports or publications, but it's a useful approximation to keep in mind, and it's helpful at this stage. To recap, for small samples, we need to use the t-distribution with n-1 degrees of freedom. Using the normal distribution or the empirical rule would make our confidence interval too narrow. Think about why that's the case in comparison to the 2 critical values I've shown you, the 2.064 for a sample size of 25 and the 2.776 for a sample size of 5. More on that here. Here's a quick comparison of critical values from the normal distribution, from the empirical rule, and from a t-distribution with a sample size of 15, so 14 degrees of freedom. See how the critical value, and therefore the bounds of the confidence interval, are going to expand as we move from the normal down to the t-distribution. On the bottom part of the slide, I give you a comparison of the t-distribution at the 95% level for sample sizes of 5, 30, and 151. Now notice, for all practical purposes, the value matches the normal distribution for the large sample of 151. Right, 1.960 versus 1.976. So with the t-distribution, our confidence intervals are wider. And this helps to account for the fact that there's more probability in the tails, less in the middle. And as the sample size increases, it becomes more normal looking. Again, there's value to using just the empirical rule as an approximation. But you need to recognize that you're trading off accuracy for computational ease. One thing hopefully you've noticed looking at all these confidence intervals is that they're generally of the same form. It's the sample mean plus or minus the critical value times the standard error. So here I've used the empirical rule as an approximation. Note one last comment about sample sizes. Larger sample sizes mean a more narrow confidence interval and more accuracy. So it's the larger sample sizes that are going to generate smaller standard errors and more statistically significant results.